Okay, it's the last normal day of class for my honors pre-calc class. Most of the hour we went over the take-home final, and now we're going to do a little bit of review. I was asked about inverses. Well, here's the first thing you'd have to know. If you had this graph, what's its inverse? It's a reflection across the line y equals x. So if you said it would reflect like this, you're right. And in case you've forgotten, this one's called exponential, and this one's called log. Do you get the difference there? The logs, I tried to give you this dumb way to remember it. It kind of looks like a tree that's blown over in the wind, because that's what a log is. When there's a log laying in your backyard, it's because it used to be a tree, but now it's blown over in the wind, and it's... Okay, anyway. So there's the log, and this one is an exponential. All right, that's an example of two things that are inverses. Do you remember having to create an inverse? Creating an inverse was where you had... Is that even in this? I don't think that's even in this chapter, though. Knowing what an inverse is valuable, but I don't think the actual process, just in case it is. Let's say I was going to make that into its inverse. Remember what switches around? X and Y switch around, and then you solve it for Y. Okay, this one already is solved for Y. We switch X and Y around, it won't be. Of course, we give you more gruesome algebra to do than just that. It wouldn't be that simple. There's probably be fractions involved and that kind of stuff. All right, other things you'd like to know. Yes, ma'am. You should know the difference between inverse and reciprocal, yes. I'm not saying that it specifically would be a question, but let's talk about it just to make sure you do know. Here is a graph. Why don't you see if you understand the difference? Inverse was the one I just did. That would be a reflection over what? Over y equals x. How about inverse? That's different. That's if this is f of x, what is 1 over f of x? Remember that? Do you remember where this one gets small, the other one gets big? Remember that deal? How about this? When it's 0, how could you have 1 over 0? You couldn't. All right, everybody sketch what you think the inverse of this red function would be. I'm going to pause for a second while you give that one a shot. Hint, there's an asymptote involved, and where the one graph is small, the other graph gets big, and vice versa. Okay, so if I wanted to do this one, I would say, where's the function right there? The function equals 0. What would its 1 over function be? The inverse of it? 1 over 0, which doesn't exist. How many of you knew there was an asymptote running right through there? Good. Okay, then, when this one's really small, like in here, the function's really small. Its y value is like 0.5 or something really small. Then the other one's going to be really big, so it's up here. Where would they ever touch each other? What's the one thing where you put 1 over it and it's the same? 1. Wherever this thing hit 1, that'd be the one spot where they would be the same. Do you get how it would never go down into negative land? Because if you have positive values here, here, then 1 over that positive value would have to stay positive, right? All right. If you understood that, if you didn't understand the right side, I would recommend you try again on the left side of the asymptote and try to figure out what that should look like. And I'm going to pause again for a second because I think some people were lost. I've graphed the right side of the asymptote. What would it look like on the left side? Okay. So where is the one spot where they'd be the same? Right there at 1. At y equals 1. At f of x is y, right? And y equals 1. 1 over 1 is 1. So, and then where this one's really small, the other one would be really big. So it'd be like that. Raise your hand if you had that part right. Okay, good. Now you remember inverses. That was a good question. All right. Now somebody asked, what about like inverse sine or inverse cosine? All right. Well, or inverse tangent. They're all the flips of the regular functions. Let's just make a quick sketch of what does regular sine look like. Just, if you don't know that one, we got to get that one down first. What does regular sine look like? You should be able to draw me a little wave. You should know where it starts. A lot of people know it's a wave, but they can't remember This one started at 0. This one started at 1. Make a really quick sketch of sine, cosine, and tangent. All right, sine starts at 0 and goes back and forth. Cosine starts at 1 and then makes like a valley, and then it does, it goes back and forth just like sine does. It's just that it's been shifted over. And last is tangent. This one's the one that's nice and centered and looks like that. And the key spots on it are pi over 2 and negative pi over 2. Okay, so how about inverses of these things? The inverse on sine, inverse sine, is where it's a reflection over the line y equals 1. It's this thing, okay? But you can't do the whole thing. Only part of sine can be inversed. From here to, I'm going to draw the rest of it in red here. That's the part that we can actually do between here and here. So that's the part of inverse sine that I could actually draw for you. And it would be a reflection across that line. So I will do it in green here. That's what inverse sine looks like, the green one. Let's flip across that line. And then do you remember that x becomes y and y becomes x? Back to regular sine again. Do you get, this is from pi over 2 to negative pi over 2. And that's why we say inverse sine only goes between negative pi over 2 and pi over 2. And its height here of 1, and it's like the lowest spot it was negative 1. Those become the x values. All right, so if I asked you for the domain of inverse sine, that would really have been the range of regular sine. What was the range of regular sine? Negative 1 to 1. So what's the domain of inverse sine? Negative 1 to 1. What if I wanted the range of inverse sine? That'd be the same as the domain of regular sine. Should have been from here to here. Cosines, if I was going to graph the one that rides on the top of sine, do you remember that one? It's not inverse sine. The one that rides on the back of sine, the sister function. What was that one that rides on the back of sine? Cosecant. That goes like this. You remember that? Okay. And it has asymptotes because where sine is 0, here, I'm going to go back to a cleaner picture. Here's regular sine. And here's cosecant. Wherever sine is 0, 1 over 0 doesn't exist. So cosecant is this green one that would go like this. And that. That's the green one was cosecant. What's the one that rides on the back of cosine? It's just like this, except, yeah, cosine goes with secant. All right. Okay, now back to this other thing. Cosine here, if I was going to find the part of cosine that has an inverse cosine, because again, inverse cosine is not secant. That's a different thing. Inverse cosine, this would be the one where we'd say, okay, where's the part that can actually have an inverse from here to here? And that little part right there is from 0 to pi, and that means inverse cosine only exists between 0 and pi. Now, we would not ask you for what the graph of this looks like. It's just the reflection over this line, but it really gets icky looking. We wouldn't ask you for that. But what we might ask you is, what's the domain of inverse cosine? So you'd have to ask yourself, okay, so what's the range of regular cosine? Okay. The range of regular cosine was from 1 to negative 1, so that wouldn't have been that tough of a question. All right, one more thing. Do you remember this graph for inverses? Where is inverse sine even allowed? I'll give you one of them. Inverse sine was only allowed, we just showed you a second ago, from pi over 2 to negative pi over 2. So it was like this, and it can touch on both ends. Why don't you try to remember where the other two big ones, inverse cosine and inverse tangent, try to remember where they can live, which quadrants they're allowed in. And don't forget, there's a dead zone. And this is where the range, because it's from the domain of the originals, it's where the range of these functions is. So when you're doing your answers, and you're like, oh, it's an inverse trig question. Ooh, two things on inverse trig. Down here, this isn't 3 pi over 2 anymore. It's negative pi over 2 if you're in inverse world. And inverse sign's only allowed there. What's the one that goes from here to here? Inverse cosine. And then the last one. What did I just do slightly wrong on this last one? Inverse tan. It's not exactly there. What's wrong? It doesn't touch, because what's special about tangent? It has asymptotes, so it can't touch its endpoints. So I'd have to slide this out just a little bit and say inverse tan doesn't touch at pi over 2 or negative pi over 2. Okay, those were some good questions. Keep on asking me stuff. What else is the topic we haven't talked about in a long time? How about plain old-fashioned circle trig? Do you want review of that, or are you good at it such that you probably don't need it? Seeing a lot of shaking heads, so okay. Again, I'll leave it to, there's a whole review video on circle trig. If that's your thing, go watch the video. Anything else? I'm trying to just jog your memory, but somebody did mention parametrics. Do you want me to say anything about parametrics? I can. What? Okay, so big picture on parametrics. What's the main thing that's different about parametrics? They have a x and a y, and what do they both, those x and y things both have in them? T. So let's say I had x equals 2t plus 6, and y equals t plus 7. Then you've got three things, x, y, and t. So if you were going to graph something, you could have a txy chart. Does that ring a bell? And at time 0, you could figure out where is my graph, and it would be at x is 6 and y is 7. See what I did there? So if you had to graph it, your best friend in graphing is still the xy chart, except it's the txy chart. All right, other things these always had was a domain. Like time had to be between 0 and 1, for example. And then what are the more complicated kinds like this? We might say take this and make it into not parametric. Do you remember what to do? Top one gets solved for t. Bottom one gets solved for t. That's easy. T equals y minus 7. Top one's a little harder. X minus 6 over 2. There, I solved them both for t. And now what do? Set them equal to each other and solve. Okay? And then you got an equation that only has x's and y's in it. Then its domain would be not x anymore, it would be t, sorry, not t anymore, it would be x. The domain of an xy equation is its x. All right, if that was something that's like, ooh, I don't remember that at all, there's a video for that. Okay, that's all I got for you for today. I'll look forward to seeing you on the day of your final. Make sure you study. Remember, there's a 2-hour morning help session tomorrow. I'll be here if you want extra help. That's all I got for you for today.